now I will move forward to the calculation of these beta 1 and beta 2 factor for our workshop. Now, once again, this diagram is taken from SP24 Appendix D. As I showed to you earlier, this is my top joint of the column and this is the bottom joint of the column. So I am going to get my value of beta 1 from this location and the value of beta 2 from this location, right? But in our case, both the values will be same because our beams framing into the column are of the same size. I am saying of the same size only. Right now, I am not saying anything about the reinforcement inside the beam because flexural stiffness formula itself is I by L. And I, my friend, is a pure sectional property of the beam, right? It is nothing but BD cube by 12. If you recall our basic theory, it is BD cube by 12. There is nothing about reinforcement in this formula. It is purely based upon the size of the beam. And as my size is same at the top as well as at the bottom, my beta 1 is going to be equal to beta. So flexural stiffness K is EI by L, but since we have got 1K value in the numerator and 1 in the denominator, we can conveniently cancel out this value of E and we will consider only I by L. So now, please pay attention that how we are going to calculate this value of beta 1 and beta 2. And I would like to add one more thing. This calculation of beta 1 and beta 2 using proper codal references, you will not find it anywhere in most of the literature or most of the books. Okay, this our research team has done a lot of research and they came up with these calculations. So let us pay attention to these calculations carefully, and if you have any doubt, then please get it cleared at the end of the session because later on you are not going to find it in any of the references. Yeah. So let us calculate the value of K for our columns and our beams, right? So when I have my when I am calculating the flexural stiffness of my column along the major axis, so obviously my formula for I will be BD cube divided by 12. So here we are calculating only the flexural stiffness K. So flexural stiffness K for the column along major axis will be BD cube divided by 12, right? Here this is the length of the column in the denominator. Now why I am multiplying this KC with 2? Because at any of the joint, if you see, we have two columns framing into that joint. Even if you see at the bottom joint, we have two columns framing into that joint. That's why the stiffness of the column at the joint, which you can also correctly say summation Kc, because we are adding both the stiffnesses together. This should be actually summation Kc. So summation Kc is 2 into BD cube divided by 12, which works out to be 2 into 0.3. Our column is 300 by 900. That's why 0.3 into 0.9 cube divided by 12 divided by 3.6. It is convenient to do this calculation in meter. Otherwise, the value comes out to be very high. So I am doing this calculation in meter, and my value of summation of stiffness of the column along major axis is 0.010. And now let us calculate the stiffness of the column along minor axis. So if you see my frame, I will just draw it for your reference, otherwise you will get confused. This is a bit confusing, so you better pay attention, right? This is our view of the frame in plan, right? This is one beam framing into the column. This crossed mark thing is our column, right? And this is our beam framing into the minor axis of the column, and this is our beam framing into the major axis of the column. Now, when I am calculating the flexural stiffness around the major axis of the column, right? When I am calculating it for this bending moment along the major axis, that time it is 0.3 into 0.9 cube divided by 12, right? And when I am calculating it for the minor axis of the column, for bending moment in this direction, at that time it is 0.3 cube into 0.9 divided by 12, and that value comes out to be 0.001. This is 0.010, this is 0.001. So this is my summation Kc along minor axis. Now, for column, my friends, we have to find out the stiffness in major direction and in minor direction. That is what we have done. But when it comes to the beam, okay, when it comes to the beam, that time there is no need to calculate the stiffness in the major and in the minor direction, because whenever you have any lateral load in this direction, that time your flexural stiffness of the beam will still be BD cube divided by 12, because when the load is in this direction, my frame in this direction is active, right? My frame in this direction is active, so it will still be the it will still be the flexural stiffness of the beam considering the depth Q, right? And when there is lateral load in this direction, that time my beams in this vertical direction will be active, and hence while calculating the flexural stiffness of the frame, the effective depth of the beam will still be D cube only. I am not going to make it B cube into D, okay, because my frame itself is changing. If my lateral load is in this direction, these two beams are going to be active. And if my lateral load is in this vertical direction, that time my beams in this vertical frame will be active, and they will still be B into D cube divided by 12. I hope so this is clear to you. That is why only in case of column, we need to find out flexural stiffness along major and along minor axis. For the case of beams in any direction, it is going to be BD cube by 12 only. Okay. But then in case of beams, we still need two values of flexural stiffness. Now, why we need two values of flexural stiffness? I will take you back to the last slide. We need two values of flexural stiffness for beam because of this classification, that for sway frame it is 1 by, for non-sway frame it is 0.51 by L, and for sway frame it is 1.5 into I by L. For these two reasons, we need to find out these two values. Now, if you see, I have found out the flexural stiffness of the beam. Once again, summation. Now, summation means I will consider this beam and this beam. Two beams are framing in my column along the major axis. So, when I calculate the stiffness of the beam for a non-sway frame, that time my flexural stiffness for beam will be this 1.2 into I by L. This is nothing but I by L. And since there are two beams, that's why this is 2. BD cube by 12 divided by L into 2. Because we have two beams framing into our column, and this 1.2 is given to us by Mr. Woods. This is where you will do wrong calculation if you don't refer to SP24 Appendix D. So this 1/2 is for a non-sway frame. Similarly, if you have a sway frame, this 1/2 or 0.5 will be converted into 1.5. The rest of the part is same. If you see, the rest of the part is same. It is still 2 into BD cube divided by 12 divided by the length of the beam. Okay. So then the calculation works out to be, this is my summation KB for a beam in a non-sway frame, and this is my summation KB for a beam in a sway frame. Okay, so right now we have assumed our frame as non-sway. So if this part is clear to you, I will wait for a moment and then I will tell you exactly which values we will require to calculate beta 1 and beta 2. I am intentionally going quite slow because I feel that this is the most important part in the workshop, because these calculations no one is going to explain you in this much detail. So now when we are assuming our frame as non-sway, that time we will require only three values of K. We will require K value of column in the major direction, this value. We will require K value of the column in the minor direction, that is this value. And since it is a non-sway frame, for the beams we will require only this value. We will need only these three values right now. So using these values, now we will move ahead and finally find out our factor beta 1 and beta 2. But here we have given you the explanation of beta factor for sway frame as well as non-sway frame in one slide itself, because then we will use these values of sway frame when we go to the ductile column. Intentionally we have kept it in one part only to avoid any confusion. So now when I want to calculate my beta 1 and beta 2 factor for the frame in major direction of the column or the joint, that time I will use Kc factor for major axis of the column, and B will be used for the category of non-sway frame. Okay. I will explain once again. For calculating beta 1 and beta 2 in the major direction of the column, we will use summation Kc of the column in major direction, and for finding and for using summation Kb, we will use the value for non-sway frame, and we end up into the value of beta 1 and beta 2 as 0.9. Now, using this value of beta 1 and beta 2 as 0.9 and IS 456 figure 26, we will find out the effective length factor K for our column. Now don't get confused. Capital K is our flexural stiffness and small k is our effective length. The notation is the same. That's why we intentionally kept it as capital K and small k. So capital K is flexural stiffness and small k is the effective length factor. So using beta 1 and beta 2 value as 0.9, I will go to IS 456 annexure E and I will show you the calculation of this. I hope so that the code is visible to you guys. Now, since we have categorized our frame as non-sway and we got the beta 1 and beta 2 factor equal to 0.9. If I draw a straight line from here and go up to 0.9 and from here also 0.9. So we are landing up somewhere in between 0.9 and 0.95. So if you do the exact interpolation using the previous values, we will get the exact value of K as 0.92. So our effective length factor, my friends, is 0.92 for a non-sway frame in the major direction. Now we will find out the beta 1 and beta 2 value for our frame type non-sway in the minor direction. So now what we will do is we will use the value Kc of the minor axis. Okay, that is 0.001. If you recall, along the major axis it was 0.01. Along the minor axis it is 0.001, because here it is 300 cube into 900 divided by 12. It is B cube into D divided by 12. So for beta 1 and beta 2 in minor axis for non-sway frame, we will use Kc of minor axis 0.001, and now we will use Kb factor same as that of the earlier value, which is that of a non-sway frame. So basically, friends, Kb value is getting governed by the type of frame. It is sway or non-sway. Okay. And your Kc value is getting governed whether you are calculating it in the major axis or in the minor axis. So if you put these values, you get beta 1 and beta 2 factor as 0.5. And now if you once again go to the same figure 26 of non-sway frame and you use the beta 1 and beta 2 factor as 0.5, then let us see what is the value of effective length factor. Now see friends, based upon the value itself, you can get a feel that if your beta factor is higher, then you are going to get a higher value of effective length. And if your beta factor is smaller, you are going to get a smaller value of effective length because your frame is somehow weaker along the minor axis. And that is why your effective length factor is also getting reduced. So let us go to the chart once again. And now if you see the value for 0.5, if I take a straight line from here and here, the value for it is somewhere between 0.675 and 0.7. So if we see the exact calculation, we end up in effective length factor equal to 0.68. Okay. So our effective length factor for non-sway frame, which is what we are going to use for ordinary column, non-sway frame, we have assumed our frame as non-sway intentionally. That time our effective length factor along major axis is going to be 0.92 and along minor axis it is going to be 0.68. If there are similar calculations for a sway frame, but I will come to these calculations when we go to ductile column. I don't want to confuse you right now, but now we are assuming our frame as non-sway and the effective length factor are 0.92 and 0.68. So now let us use these effective length factors and calculate the most important thing, that is the slenderness ratio of our column. So now if I go to the next slide, here we have calculated the slenderness ratio of our column. Slenderness ratio is nothing but the effective length factor K into the unsupported length of the column divided by the lateral dimension of the column. If you are calculating slenderness ratio along major axis, you have to consider capital D. And if you are calculating slenderness ratio along minor axis, you have to consider B. Hence 0.92, which is nothing but the effective length factor that we got here, 0.92. Using this value, we get 0.92 into unsupported length of our column 3000 divided by the dimension of the column along its major axis 900. And hence our slenderness ratio, my friends, comes out to be 3, which is less than the value of 12. And hence we can say that my column is not slender because our slenderness ratio is coming out to be less than 12. Similarly, if we take the value of K as 0.68 and we take the dimension of the column along minor axis, that is the width of the column, we end up into the slenderness ratio as 6.8, which is also less than 12. And hence once again our frame or our column, you can say, in the minor axis is also not slender. So we have to calculate whether our column is slender or not slender separately for the major axis and minor axis. So in our case, our column is not slender in major axis as well as in the minor axis. Hence, we can conclude that as the columns are not slender, additional moments MA shall not be added. The references of these are given in the later part when we are giving preferences and override in Etabs. That time the references are given. But I think all of you know these terms, that slenderness ratio is less than 12, hence our column is not slender, and so we will not add additional moments to our analysis moment in order to find out the design moments, right? Our first step in Etabs is to find out design moments based upon the analysis moment. Once we get that design moment and design forces, then we calculate the reinforcement. That part is easy. Calculating the design forces from analysis forces is a tricky part. Calculating reinforcement is easy. You can use SP16 and find it out. But finding out the design forces from analysis forces is important. So here we will not add additional moment to our column. Hence, the design moment for my column along minor axis will be maximum of analysis moment plus minimum eccentricity moment, or this should not be plus actually here. This should be comma. Very sorry, we will correct it later on. Design moment along minor axis should be maximum of analysis moment or eccentricity moment, and whatever is that value, it will be added to our additional moment due to slenderness. Maximum of these two will be added to our moment due to slenderness. But right now our moment due to slenderness is 0 because our column is not slender. So MA is 0, and hence our design moment will be simply maximum of analysis moment and minimum eccentricity moment. So I will go back to the second slide of column where we have calculated minimum eccentricity moment. So the minimum moment along minor axis is 48, which is obtained from analysis. This is analysis moment, and the eccentricity moment is 93. So the maximum of these two is my design moment. So obviously it will be 93. Similarly, along the major axis, the design moment will be maximum of analysis moment and eccentricity moment. So it will be maximum of 42 and this 168. So my design moment along major axis will be 168. So simply these 93 and 168 will be our design bending moments. So our design bending moments are nothing but, sorry. So our design moment along minor axis is 93. But as we discussed earlier, minimum eccentricity, we can consider it about one axis at a time. So we are considering it only about the minor axis. We are not considering it about the major axis. So along the major axis, simply the design moment is nothing but what we got from the analysis. So our design moment along minor axis will be 93 and along major axis will be 42. So these are my design moments. Now I will take these moments forward and perform my calculations for calculating the reinforcement, right? So this is quite easy. We have studied it in the academics also, how to design a column which is subjected to axial force and biaxial bending, right? So we have to use interaction curves for this part. I will quickly go through it if you allow me, because this is given in any basic book. By referring SP16, just to save time so that we can cover the parts later on in more detail. So referring SP16, we assume our percentage of steel as 2%. We find out the ratio of P by FCK which is actually given in the code in the form of rho by FCK. So this rho by FCK value is 0.06 if we assume percentage of steel as 2%. So in any calculation of column subjected to biaxial bending, you have to assume PT initially, okay? And then you have to perform those iterations. So assuming PT as 2%, our P by FCK value is 0.06. Our value for D dash by D, which is the effective cover divided by the dimension of the overall dimension of the column in that axis, along that axis, 60 by 900. Right now we are calculating it along the major axis, so we have taken 900. That will be 0.06. So in SP16 there are different charts given for this value of D dash divided by capital D. So right now my value is coming out to be 0.06. So I will use a chart which is higher than that value, and that is 0.10 wala chart. So we will use D dash by D 0.10, and from that chart, using the value of PU by FCK BD, we will find out the value of MU by FCK BD square. So here what we are doing is we are assuming some value of PT. We are calculating a factor based upon our axial force, and we are finding out our bending moment capacity of that column. Okay, we are doing a reverse calculation. We are assuming the PT, calculating the factor of PU by FCK BD, and from that we are working out the bending moment capacity of our column. And now our factor of PU by FCK BD comes out to be PU by FCK BD comes out to be 0.57. So if you refer this chart of D dash by D 0.8, you use this value of PU by FCK BD 0.57, you can find out the value of MU by FCK BD square, which is 0.04. So I will just show you how it, just for one value, I will show it to you. The chart, the actual chart, 48. Yeah, see, this is the actual chart 48. So if you see on the x-axis, sorry, on the y-axis, we have this value of PU by FCK BD. We have these different curves for the value of rho by FCK. We have different curves for the value of rho by FCK. And from that, if you go from here to here, you get a value of MU by FCK BD square. So our value of this was 0.57. Right? So if you go from 0.57 and if you go to the rho by FCK value of 0.06, you come down to the value of MU by FCK BD square. See, this is 0, this is 0.1. So this half value is obviously 0.05. So we are somewhere getting the value equal to 0.04, right? We are somewhere getting the value equal to 0.04. So our value of MU by FCK BD square from the chart is coming out to be 0.04, right? I have shown you how we got it from the chart. So if you use this value of MU by FCK BD square 0.04, and if you input these values of FCK B and D square, you simply need to, if this is your MU and you have this value of FCK BD square, I'm just showing this for the college students to recall. Practicing engineers obviously know this. So if you simply take all these terms in the denominator on the right hand side, and if you multiply them with 0.04, you end up into your bending moment capacity for this much amount of reinforcement as 292 kilonewton meter. This is your bending moment capacity, my friends. Okay. And similarly, if you perform the calculation for other axis, that is minor axis of the column, your value for D dash by D will change, obviously, because this denominator will change. Here it was 900, here it will be 300. This we have to do because we are performing calculation for a column subjected to biaxial bending. Column has got bending moment along major axis as well as along minor axis. So we have to find out capacities along major axis as well as along minor axis. So for finding out the capacity along minor axis, we have to use this value 300. d dash by d, it comes out to be 0.2. Now we in the SP16 we have a chart for this value of d dash by d, which is chart number 50. Here it was chart number 48 for d dash by d equal to 0.1. For d dash by d 0.2, the chart changes. It is chart 50. And if you find out PU by FCK BD, which is same, my friends, PU by FCK BD will not change. So for the same value of PU by FCK BD 0.57, if you refer chart 50 and you use the same value of rho by FCK 0.06, you end up into the same value of mu by FCK BD square, which is 0.04. I am not showing you the calculation intentionally to save time. I have shown you the calculation for this 0.04. But if you go to chart 50 and if you cross check, you get the same value of mu by FCK BD square, which is 0.04. But now our value of bending moment capacity, my friends, will change, because here it was B into D square. Okay, people ask us this doubt that, sir, if my value of mu by FCK BD square was same, PU by FCK BD was same, PT, the rho by FCK was same, still why this value is lesser? My friends, this is because we have to consider 300 square into D. It is D square into B right now. Okay, when you are calculating about the minor axis, hence it will be 97.2, lesser than this. So now we have found out our bending moment capacities using the assumed percentage of steel. And now I think this is very much known to everyone, because this is in our academics itself and it is given in detail. Now we have to find out the value of PUZ, referring to chart 63 on page number 148 of SP16. So if you find out this value of PUZ, which is also given to us by a formula 0.45 FCK AC plus 0.75 FY ASC. So here 0.45 is the empirical factor. FCK is our concrete grade. 300 by 900 is our size of the column. 0.75 is again an empirical factor. FY is 500 and ASC is calculated based upon the assumed percentage of steel 2%, and that is 5400. So if you input these values, you get the value of PUZ as 5670 kilonewton. Now this PUZ will be used to actually design our column subjected to biaxial bending. So we find out this value of PU by PUZ. This PU is nothing but our design axial force, 4673, if you recall. 4673 is our design axial force. This is our factor PUZ. We get the value of PU by PUZ as 0.824. And similarly, if you calculate this factor MUX by MUX1, where MUX is our design bending moment and MUX1 is our bending moment capacity for that much percentage of steel, we get that factor as 0.143. Now, if you similarly calculate MUY by MUY1, this is design bending moment along minor axis, and this is the capacity of the column along minor axis, we get this factor as 0.956. Now, how to check whether this assumed PT is correct? We have to go to chart 64, page number 149, and we have to perform a reverse calculation. So what we will do is, we will consider our value of MUX by MUX1. I will clear the slide. We will consider this value of MUX by MUX1, which is 0.143, and the value of PU by PUZ, which is 0.824. And by reverse calculation, I will check what is my value of MUY by MUY1, which is given in chart 64. So if I just for your reference, we have shown this value for one case only. Next time I am directly going to skip this part. So my value of MUX by MUX1 was my value of MUX by MUX1 is 0.143. So see, This is 0.1, this is 0.2. The center is obviously 0.15. So we are somewhere here, 0.14. So if you go upwards, and we have assumed our PT and found out our, we already have this value of PU by PUZ with us, which is nothing but 0.824. So if you go to 0.824, which is actually the maximum value itself is 0.8. So it says that PU by PUZ greater than or equal to 0.8, you have to use the last chart. So if you go to the last value and if you connect it to here, you end up in a value of MUY by MUY1 somewhere between 0.95 and 1. If you do the exact calculation, then you get the value of MUY by MUY1, the permissible value, as 0.97. And if this value is higher than what you get for your design forces, you can say that your assumed percentage of steel is correct. In case if your this value is lesser than 0.956, you have to once again perform this calculation using a higher value of PT. And for whatever value of PT you get this value higher than this, you can say that your percentage of steel is okay. Okay. Now, how much margin to keep in the design? It depends upon the designer to designer. But if you see Etabs, it gives you very, a design without any margin. See, our permissible factor was 0.97 and our design value is 0.956. It is very close. Etabs is not keeping any margin. So as a designer, it is your call how much margin you want to keep in your design. But Etabs will, Etabs will not keep any margin in the design. So this way, my friends, our design for flexure for an ordinary column manual calculation is finished. So now let us see, we got 2%. Now let us see what Etabs is getting in the design. See, if you see the design calculations, it is taking 1.97. If you take the exact values of the design moments and perform all the calculations to the decimal accuracy, you end up into the rebar percentage as 0.97. So we assumed it as 2% and performed our calculations, and we found that our results are matching with that of Etabs. So this, my friends, ends the calculation of manual calculation of column in flexure. Now let us see the calculation of the column in shear. So let us design our column for shear. So if you recall in our the diagrams of the shear forces, if you want, I will go back to that slide from where we extracted our analysis forces. So see, here we have the value of shear force as 28 kilonewton approximately in the minor axis and 24 kilonewton approximately in the major axis. Now, my friends, for our for saving our time, we will perform the calculation about one axis only. So that's why we have chosen the higher value, and that is 28 kilonewton. So our analysis shear force is 28 kilonewton, and please pay attention. Please pay attention. It is along the minor axis because it is going to make a difference when we design the column manually. So this 28 kilonewton is along the minor axis of the column. So let us take this value of analysis shear force 28 kilonewton and find out the value of design shear force. Now, when you are designing an ordinary column, the analysis shear force and the design shear force, they are same. Okay, like we did it for the beams yesterday. When we were designing ordinary beams, the design shear and the analysis shear was the same. But when we went to the design of ductile beam, if you recall, due to the formation of plastic hinges, the code was asking us to use slightly higher shear force in the design than what we get from the analysis. But for the ordinary beam, it was the same. For the ductile beam, it was asking us to increase the shear by some amount.
Welcome you all in ISO certified live training program, Etabs, RCDC and Excel that makes you a professional structural engineer. In this training program, you will learn everything about Etabs and RCDC from basic to advanced, real life project of medium rise structure from architecture plan to final design sheet, real life project of high rise structure with all advanced topics, design of structural elements using advanced Excel sheets. Have a look over the features of this training. Daily live classes conducted by expert for 1.5 hours. Recording of every session with lifetime access. Can interact with expert anytime, 24/7. Exposure to real practice. ISO certification of training completion. It's 5-star rated training program. Till now more than 1,000 participants have benefited from this training program. Now you are the next. Hello everyone, welcome you all in a new ISO certified live training program, design of substructure using CSI Safe, Excel and manual. In this training program, you will learn all about the concept of substructure design, commands in CSI Safe software for the substructure design, validation of CSI Safe result with your manual and advanced Excel sheets. This training program will cover 4 real life projects. In the first and second, we will cover all the types of isolated foundation in CSI Safe software. In the third real life project, we will cover the raft foundation. And in the fourth real life project, there will be the coverage of pile and pile cap design of basement wall, and at the end of this training program you will learn how to prepare the final design sheet for the site execution. Have a look over the features of this training. Daily live classes conducted by expert. Recording of every session. Can interact with expert anytime. Exposure to real practice. ISO certification of training. It's 5-star rated training program. Till now more than 1,000 participants have benefited from this training program. Now you are the next.